Welcome to Math 331 problem solving. This is lecture 25. And so what we're going to do today is we're going to do proof by story, and then we're going to shift gears and start talking about probably not project Euler problems. I'll change that later to Putnam. And I can fix that later on the PDF. Okay, so we talked a little bit about some of the first two results here. So here are a couple of things you can prove by stories. The first is the features theorem, and this is n choose k is equal to n choose n minus k. Then there's Pascal's identity, n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. Then there's the binomial theorem, x plus y to the n equals the sum k goes from 0 to n of n choose k, x to the k, y to the n minus k. And then, there's some other ones, sums of squares of binomial coefficients. Probably should have left more space. The sum k goes from 0 to n of n choose k squared is actually nice. And then the cookie problem, how many ways can you divide C cookies among P people? And then there are applications to solve for stuff like this. And of course, n choose k is n factorial over k factorial n minus k factorial. So I know we've done a lot of these already. I want to quickly redo the first two problems, or maybe just the first problem, just to have everybody on the same page. I know I've asked this before. How many people have read Dr. Seuss's The Sneetches? Okay. It's now a business expense. Excellent. Okay, no, I have a copy at home. So let's do the Sneetches theorem. And this is n choose k is n choose n minus k, with n choose k n factorial over k factorial n minus k factorial. And I will assume that anybody who's watching this video knows what the factorials are. And I'm not going to say, well, no, I will say that n factorial is n times n minus 1 all the way down to 1. 0 factorial is defined to be 1. Why is 0 factorial 1? It's good notation. N factorial is n times n minus 1 dot 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 3 times 2 times 1. And we normalize, so 0 factorial is 1. There's one way to do nothing. How many ways can I order? I can't order things in multiple. I can't order nothing in multiple ways. Now, as a fun fact, you can extend, and negative 1/2 factorial is the square root of pi. So there's an extension of the factorial where you don't have to put in an integer input. I am not saying the number of ways to order negative 1/2 of a person is the square root of pi. I'm saying this function agrees with the factorial function on the positive integers, or actually the non-negative integers. So let's prove that n choose k equals n choose n minus k. So we're going to compare n factorial over k factorial n minus k factorial versus n factorial over n minus k factorial n minus k factorial. But what is n minus k factorial? K factorial. So this is the same as n factorial over n minus k factorial, which is the same. And that's the proof. So one way you can prove this is just straightforward algebra. And this kind of suggests what's going on. The story proof choosing exactly k from n to take is the same as choosing exactly n minus k from n to exclude. If I'm choosing k people from n to be on Team Sneech, the ones that are going to have stars on their belt. So if I choose k Sneeches and only k Sneeches to get stars, then how many Sneeches are left? N minus k. This is the same as choosing n minus k Sneeches not to get a star. So you can prove this identity by telling a story. So much of combinatorics comes down to this. Can you tell a story? And if you can, you've got the result. I'm starting with easy ones, and we're going to get to more interesting ones later. So the next is Pascal. We have n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. So we want to compare n factorial over k factorial n minus k factorial plus n factorial over k plus 1 factorial n minus k plus 1 factorial versus n plus 1 factorial over k plus 1 factorial n plus 1 minus k plus 1 factorial. I'm just substituting in. I'm going to do a purely algebraic, no intelligence, brute force proof. What should I do to both sides?
Sum the left side.
I could try to sum the left-hand side. What could I do to make it easier first? So I could, everything has an n factorial. So let's multiply through by, and we'll have an n factorial in the denominator on both sides. What should I put in the numerator?
K factorial.
So definitely k factorial. Everything has at least a k factorial. And what about everything else?
N minus k.
Not everything does not have an n minus k. The first term,
Plus one.
n minus k plus 1, or, so however you want to write it, right? N minus k plus 1 factorial. And so this yields, so when I multiply through, the n factorial cancels, the k factorial cancels. I've got an n minus k plus 1 over an n minus k. So I think I just get a 1 over n minus k. So I get a 1 over n minus k. And for the next term, the n factorial cancels. I've got a 1 over k for the first one, but that's it. Because the n minus k plus 1 cancels. I'm sorry, 1 over k plus 1, thank you. And you see how easy it is to make an algebra mistake, right? And then on the other side, I'm going to have an n plus 1. I'm going to have a k plus 1 that survives. And I'm going to have an n minus k. Because n plus 1 minus k plus 1 is just n minus k. At this point, things are looking really good. Because you can see now when I combine, I get k plus 1 plus n minus k over n minus k, k plus 1, which is just going to be equal to n plus 1 over k plus 1 n minus k. And so this proves Pascal's formula by pure brute force computation, right? The proof by story, we could have, say, n Sox fans, 1 Yankee fan, and we need to choose k plus 1 people. And so if I just consider Yankee and Red Sox fans just as people, which I'm willing to do for the sake of mathematical exposition, we have n plus 1 people, and I need to choose k plus 1. And then I can split this on two possibilities. Either I'm in the good case where I have no Yankee fan chosen. That's 1, choose 0. And then how many Sox fans do I need? I need k plus 1. Or I chose the Yankee fan, and now I have to choose, I only need k Sox fans. And so this would be the proof by story. So when we did the algebra proof, do you have any sense why it's true? We just multiplied everything and it worked out at the end. The most important thing is to know if you have a true result. And then once you have it, can you come up with a good proof as to why is it true? And so step 1 is just prove the damn thing. All right, so the algebra proof works. Thank you for catching the 1 over k plus 1 mistake. But it gives me no insight as to why it works. The proof by story is telling me what's going on. And if you notice, the tops always add up to n plus 1. And the bottoms always add up to k plus 1. And what that's telling you is that most of the time, we don't include these two factors because they're both 1. You normally don't write times 1 in mathematics, but it would be useful to include that to see where Pascal's formula is coming from. It's a little bit more clear when you put in those ones in terms of what's going on in terms of choosing. All right, so we're doing different proofs by story. We did Sneetch's, we did Pascal's identity. The next is the binomial theorem. And so is everybody comfortable with the binomial theorem? So this basically says if we have x plus y to the n, this is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k, or we could do n choose k, x to the n minus k, y to the k. I could use either one. It makes no difference because of the very first result we proved, that n choose k is the same as n choose n minus k. One way you can look at this, basically proof by story. X plus y to the n is x plus y, dot, 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 x plus y, x plus y. So for each term, we choose either an x or a y. So when we expand, have only terms of the form x to the let's say k y to the m. But what can you tell me about k and m?
They have to add up.
What do they have to add up to? So we know with k plus m equals n. And what can you tell me about possible values for k? 0 to n. And 0 less than equal to km less than equal to n. So we know that it equals something of the form sum k goes from 0 to n, a sub kn, x to the k, y to the n minus k. We know it has to have a form like that. And if you think about it, what's going on? We have to choose exactly k of the n x plus y terms for the x. Remaining give y. So how many ways can we choose the k factors that give us x? I'm sorry? No. We want to have exactly k of the n terms giving us an x. So we have n factors. and exactly k of them have to give an x. How many ways can we do that? Yeah, just then choose k, right? We have n factors. For each factor, we choose either an x or y. I'm looking at the term x to the k, y to the n minus k. So I had to choose x exactly k times. So that's going to be n choose k. Now, how many factors are left that I haven't chosen x from? So how many factors are left? N minus k. And for each of them, I have to choose y. How many ways are there to choose n minus k from n minus k? One. But how should I write that one?
N minus k over choose n minus k.
N minus k, choose n minus k. And nobody writes that. Everybody just writes n choose k. But really, when you're looking at the binomial theorem, it really is the sum, k goes from 0 to n choose k, n minus k choose n minus k, x to the k, y to the n minus k. This is just yet another example of not writing some factors. But if you think about what's going on, we really have this n minus k choose n minus k. This is not that important for the binomial. Are there any Seinfeld fans here? Seinfeld is a great show about nothing. If more people knew Seinfeld, I would have made that joke when we were doing zero factorial. There's one way to do nothing. One of the most brilliant episodes of Seinfeld is the opposite. So George Costanza is the epitome of a loser. And in this episode, he remarks that every decision he's made in life is wrong. And so they convince him that if every decision you've made is wrong, the opposite must be right. You should do the opposite of your instincts. Now, what's wrong with that in life?
It's not one or the other.
Yeah, usually it's not one or the other. Usually there's multitudes of possibilities. But if you're flipping a fair coin, if it's not heads, it's tails. So and this actually comes up in information theory. If you're flipping a coin, let's say it's a heads is a 1, a tail is a 0. And you want to make sure that you transmit information correctly. And let's let P be the probability of an error. What's the best probability of an error if you're transmitting? 0. Right. What's the worst probability of error? 0.5. Why isn't it 100%? Because then you could do the opposite. So if you know the coin is always wrong, it's essentially the same as the coin is always right if you just negate it. And so if you've seen the multinomial coefficients, if you've seen multinomial distributions, these come up in probability and statistics. Now, all of a sudden, once we have 3 alternatives, then things are a little bit more complicated with the story. And you can define the multinomial coefficients in terms of repeated applications of binomials. All right, so the next, I don't think what name I want to give this down. We'll call it the socializing All right, do you want to do baseball teams or colleges? Colleges. All right, I need a great school. Williams. So we have N people from Williams. And it's very easy to give me an inferior school because almost anything would work. Any choices? Sorry, what was that?
Amherst. You meant Amherst.
The Amherst Harvard Michigan Consortium. And I assume we don't really care about Wesleyan. And we don't care about Middlebury. So we have N people from Williams and people from the Amherst Harvard Michigan Consortium. Okay. And I want to, what is the sum k goes from 0 to n of n choose k squared. Does anybody know what that sum is? Good. What should your first instinct be if I give you a sum that you don't know?
I know the sum I know is that if you just sum them, it's going to be 2 to the n.
So that's related to the binomial theorem. In the binomial theorem, note, if we take x equals y equals 1, then x plus y to the n is just the sum k goes from 0 to n of n choose k, and that's going to be 2 to the n. And similarly, if you take y equals -1 and x equals 1, you get the alternating sum of the binomial coefficients is 0. So those are nice, those are very nice identities that come from the binomial theorem. Good. So I'm glad that nobody knows this. We've now finally reached something that you don't know. How could we find out what this is? What should we do? '21st century, you should have instincts by now on what you should do.
Expand the square using the definition of n choose k.
So you could put in what n choose k is. You're gonna have a lot of factorials. How could you get a feel for what the answer might be? What could you do? You could try some simple examples. Gather data. You need to have Pavlovian responses, right? Whenever you see a product, you should always be thinking take logarithms. You should always have a list of things to try. Is this an induction? Is this a story? Is this... Whenever I'm giving you what is the following, compute some terms and see if you can detect a pattern. Once you know what you're trying to prove, it's often a lot easier. Frequently, if you know what the answer is, that gives you an insight. Oh, okay, maybe if I look at it this way, how can I get something like this to show up? So let's put in some values. Let's gather data. When n equals 0, what do we get? We get 1. So when n equals 1, we're going to just sum 1 choose 0 squared plus 1 choose 1 squared. We get 2. Is this enough data? Not even close, right? N equals 2. Now it's a little bit more interesting. So when it's 2, we're going to be 2 choose 0 squared plus 2 choose 1 squared plus 2 choose 2 squared. Well, really what we're doing is we're just squaring rows of binomial coefficients, right? So this is just 1 squared plus 2 squared plus 1 squared. That's just 6. Any guesses? 1, 2, 6.
Oh, a double, then triple, maybe quadruple.
Right. So what would that be? 24.
I feel like we've seen that.
So 1, 2, 6, 24. What sequence is that?
And multiplication. There's not.
1, 2, 6, 20. It's the factorials. The answer is just n factorial. Should we calculate any more, or do we all agree that it's n factorial?
Let's do one more.
Let's do one more.
Wait, n plus 1.
Okay, n plus 1 factorial. So let's look at n equals 3. And so now it's just going to be 1 squared plus 3 squared plus 3 squared plus 1 squared, right? Uh-oh, that's 20. That is not 4 factorial. And if we do n equals 4, 1 squared plus 4 squared plus 6 squared plus 4 squared plus 1 squared. So 4 and 1 is 5, 10. Oh, no, sorry, 16. 1 is 17. 17 and 17 is 34. Plus 36, 70. 1, 2, 6, 20, 70. We could do another one, but again, part of this is I'm trying to give you an idea of how to, do any of these numbers look familiar? Do you think factorials might play a role in the answer? We have a lot of combinatorics going on. We have a lot of binomial coefficients.
It's the growth rate is lower than the factorial.
Right, because we would have gone up to 24, then we would have gone up to 100 or 80. So the growth rate is slowing down. So
Even if it's factorial over something.
So does everybody memorize Pascal's triangle up to row 100? Can you calculate it quickly? Yeah. Because you just have to add the stuff above, right? 1, 1, 1, 1, 2, 1, 3, 3, 1. I mean, I think what's slowing me down is just the time of writing. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. I feel like a typewriter. 1, 7, 21, 35, 35, 21, 7, 1. Ah! I mean, I'll finish writing.
Skipping. There's middle, but skipping.
Yeah.
So let's see what we're noticing. We've got the 1, the 2, the 6, the 20, the 70. So this was the answer when n equals 0. This was the answer when n equals 1, n equals 2, n equals 3, n equals 4. And this is row 0, row 2, row 4, row 6, row 8. And again, you can easily tell what row it is by looking at, these numbers here. So what do you conjecture? The sum, k goes from 0 to n, of n choose k squared, what would you conjecture?
To n choose n.
Just you can choose n, and that's the correct answer. And so we got to this by looking at some data. And again, the more things you know, the more likely you are to see connections. Feynman was great at seeing connections, partly because he knew so many different things. All right. So now how do we prove this? So proof that the sum, k goes from 0 to n, of n choose k squared is 2n choose n. And remember, a long time ago, I said we have n from Williams, and we have n from the Amherst Harvard Michigan Consortium. How else can you write n choose k? What was that? N choose n minus k. What was the very first thing we proved today? That they're equal. You're foreshadowing. How many of you have heard of Chekhov's gun? So if you talk about a gun in scene 1, you're supposed to fire it by scene 3. You don't have that much space. Things aren't wasted. And so I wanted that identity for right now. I really do plan some of these lectures. A lot of it is deliberately unplanned, so it's what you guys are interested, but there are some things that are thought of ahead of time. So here's the proof. The sum, k goes from 0 to n, of n choose k squared is the same as the sum, k goes from 0 to n, of n choose k, n choose n minus k. Do we agree that this is true? I'm just using the Sneetch's identity. Have you guys at least read The Cat in the Hat? Okay, I got into Cat in the Hat off with a colleague of mine, Joe Silverman at Brown. And I can do the first quarter without any pausing. He's got grandkids. He's had so many more years of reading it than me that it was, I kept up with him for a while. But now, how can we view this? Give me a story. Tell me a story about n choose k times n choose n minus k. And the characters in your story are n budding mathematicians from Williams, and then I don't care who they are, from the Amherst Harvard Michigan Consortium. How could you view n choose k times n choose n minus k?
Choosing K for
Good.
minus K from K.
And how many people do we have in total? No, you've got this horrible accent today. You've gone through now so much of the extra credit you have from the memes you've sent. You might still have one in the bank, but I mean,
I'm down.
I don't know if you're done. I don't know if you did 2 or 3. So this is the same as we choose exactly k from Williams. We choose exactly n minus k from the Amherst Harvard Michigan Consortium. And then we sum over all k. What do we get when we sum over all k? Give me a story for the whole thing. So you gave me local stories. You gave me n+1 stories. On night k, and like good computer scientists, we start counting a k equals 0. On night k, we chose k people from Williams and n minus k from the other places. If you add them all up, what is this equivalent to doing? Every night, how many people have we chosen? N. And how many people are available to choose from? So what's the story? So we are choosing exactly n people from 2n people. The number of ways is just 2n choose n. This is a proof by story. Then the question becomes, what do you study next? What's next? Is it the sum k goes from 0 to n of n choose k cubed, or something else? One of the big things I want you to think about is, where is the miracle? What works, what doesn't work? And in this case, I could write it as n choose k squared. But am I really computing n choose k squared? Maybe I could say is I'm choosing k people from Williams and I'm choosing k people to exclude from the Amherst Harvard Michigan. No, I'm not choosing people to exclude. I'm choosing n minus k people from the Amherst Harvard Michigan Consortium. And so the question is, what would be the natural story for, say, a product of 3 terms? And I'm deliberately not going to tell you. I want you to think, what might be nice? We've done a special case now. Now that you know this, how can you generalize this and sniff things out? Pascal's triangle was very useful. We might need to use a multinomial pyramid too. It's going to get a lot worse. But maybe you just look down and maybe things become nice. If you notice over here, for most of Pascal's triangle, I don't need it for this problem. I just need to look straight down. What is 2n choose n? Okay. We could do the cookie problem, or we could do a Putnam problem. I think I want to do a Putnam problem just because I want you to be looking at Putnam problems for Wednesday. And I want to just go through the thought process of how would I tackle one. And since one of you was kind enough to say you found something exciting or interesting, let's do that one. So this is, I think, problem A1 from 2017. Let S be the smallest set of positive integers such that the following three conditions hold. 2 is an S. The number n is an S whenever n squared is an S. That's not the kind of condition you want. Normally the way you tell if something is in your set is you look at the stuff before it, and you use the stuff before it to determine whether or not it's in. Here, I'm telling you n is in if n squared is in. And n plus 5 squared is an S whenever n is an S. Which positive integers are not an S? And again, S is the smallest set that satisfies these conditions. When you look at this, which numbers matter? So which numbers do you think matter? Which two? Both, right? So when you're looking at a problem like this, and this is one of the things that's a little bit annoying, is they've given you 2 in 2 different places, so I'm not quite sure what the 2 dependence is. So this 2 matters. I'll use different colors. So I'll do this 2 matters. I'll do this 2 matters. And what else matters? The 5. So my first question is, how important are those numbers 2, 2, 5? If I change them, what happens? So what happens if change? So a lot of times they deliberately choose problems to make something nice happen or not. Later, I might share my favorite problem one of my favorite problems that I ever created. And I don't want to say more about it now than this. So we want to gather. I slept. What was I saying?
We want to gather data.
We want to gather data, right? So step 1 is always gather data. Start by gathering data. And so I cheated. I wrote a computer program to do some investigation, but you shouldn't have to do this on a Putnam problem. A small data set should hopefully be enough. So we want to try to figure out what is in the set. And we have a couple of rules. So we know 2 is in S. Do we get anything else in S?
We know 49.
Nope. Oh, wait, let's see.
2's an S, so then 2 plus 5 squared must be an S.
So 2 plus 5 squared must be an S, right?
Yeah.
So now we know 2 plus 5, 7, so we know 49 is an S. And maybe I'll write that in blue. And now that we know 49 is an S, what do we know?
7 is an S.
7 is an S. What else do we know? I'm sorry? So we now know 54 squared is an S. Let's leave it as 54 squared. And 54 is an S. Right, and so if we're looking at it like this, it's getting a little hard and confusing to keep track of what's going on. So what happens is we have numbers that generate different things. So 2, what does 2 give us? 2 gives us 49, because you get 7 squared. And what else does 2 give us? So it's a question of how do you, okay, so we can say 2 just gives us 49. So 2 gives us 49. Now that we have 49, what happens?
We get 7.
We get 7. And what else? That's now we get 54 squared, right? And from 7, what do we get? So we get 144. And what else? Which is 12 squared.
Nothing.
Nothing else.
And that's it. So if that's it, then maybe we should write it this way. So 2 gave us 49, and 49 gives us two things, 7 and 54 squared. 7 only gives us 144. What about 54 squared? What does that give us? Gives us 54, and I'm not sure if you can read it, that was a 54. What's the next number?
54 squared plus 5 squared.
Right, so 59 squared.
No.
No?
Because it's
Oh, sure, you're right, sorry. It's 54 squared plus 5 whole thing squared. Now for 144, what does that give us?
12.
Gives us 12. Does it give us anything else?
Yeah. It was
And then from 12, how many things does 12 give us? Just 1, right? What's the only thing 12 is going to give us? 17 squared. And then the 17 squared will give us 17, and then 17 squared plus 5 squared. So again, I'm not sure if this is the best way to attack the problem. I'm trying to write things in like a tree structure to get a sense of where things come.
Is this an infinite sign?
So this will be infinite.
Yeah.
And so in fact, you can see an arithmetic progression. 2, 7, 12, 17. And those will just march down.
But you wouldn't get to a place where it like repeats.
So for some of the stuff, it's getting larger.
Yeah. So that wouldn't repeat.
And then for the other one, when you're taking the screw, it's getting smaller. Could it get smaller to something that you've already seen?
I guess not, because you're squaring something larger.
Well, so
Well, it actually could if something's like to the power 4.
good. So the question is, what if something is to the power 4? So, and again, we're not going to solve this problem today. We'll finish it on Wednesday. But let's look. We know we have an arithmetic progression. We have 2, 7, 12, 17, 22, 27, 32, ... So the question is, are any of these a fourth power? Because if one of these was a fourth power, say 2 plus 5m equals a to the 4th, right? A to the 4th is a squared squared, so a squared is an s, and then a is an s, right? So we would get not just the square root, but the square root of the square root is also an s. So do you think 2 plus 5m could ever be a fourth power?
well, definitely not the ones ending with 7, but maybe the ones ending with 2.
So what can you tell me about a fourth power? So this is where you should immediately be thinking congruence arguments. We did this earlier in the semester when we were looking at writing sums of squares, and could you have two different sums of squares that sum to the same integer? I was really hoping somebody would want to write that up, but it's all right, I'll be teaching for more years. What do you think would be a good modulus to look at for this problem? We have 2 plus 5m equals a to the 4th. What should I look at both sides mod what? Look at the remainder when you divide by. 1 is when you divide by 2 because it gets rid of the 2 and then you just cycle through 5m. 5 is the same as 1 mod 2. So then you just get all possible values on the left-hand side. So it's not bad to try 2, but 2 is not going to work. What's left to try? Nope, there's a really natural thing to look at where the left-hand side is really nice no matter what m you choose if you look at it modulo the right thing. Not 10.
7.
I'm sorry?
7.
Not 7. So no, I'm sorry? 5. What is the left-hand side when you look at it mod 5? 2. So note the left-hand side is always 2 mod 5. And if we look at a and then a to the 4th mod 5, if a is 0, 1, 2, 3, or 4, what's 0 to the 4th mod 5? That's just 0. What's 1 to the 4th mod 5? 1. What's 2 to the 4th? 2, 4, 8, 16. 1. 3 to the 4th? So you can view 3 as the same as 5 minus 2. So it's the same as negative 2 to the 4th. We know 2 to the 4th is 1, it's 1. You can view 4 as just negative 1 mod 5. So what's 4 to the 4th? Well, you can notice it's 256. It's just 1. Is there ever going to be a 4th power that's 2 mod 5? No solution. So this is the way to do some number theory for this problem, is when we're looking at the infinite chain generated by 2, we know that there's going to be no 4th powers encountered. Right. So this may not be the best way to solve the problem. It's at least a way to start. It's a way to start gathering data. It's a way to get some sense of what's going on. And then the question is, how do you want to present information? When we started writing the set, oh my God, how do I put things in? What comes next? How do I order things? Trying to do things as a tree structure, to me, just looks like a nice way to view things. All right, so this is a good place to stop.